All right, physics students, as you can see, I have sketched the picture that is number 7 from Unit 5 Worksheet 3 of the car at the cliff. Now, I know you probably haven't been able to sketch something that looks quite this good, but do your best. And notice all the parameters that we know about are included. We know the car is 1,000 kilograms. We know the rock that was tied by a rope to the bumper is 50 kilograms. And we know the car is 10 meters away from the edge of the cliff. So, let me, I guess, kind of just get started on here and hopefully be able to explain how this is supposed to go. There's more than one way to look at this. I'm going to try to, well, I don't know what I'm going to try. But at this point, what you should do, you should sketch a force diagram. First of all, get this picture drawn. If you haven't already, draw the picture. So pause the video if you have to, get the picture drawn. And then I want you to sketch the force. I'm okay, don't worry. I want you to sketch the force diagrams of both objects. Again, we haven't had two-body problems for a bit. It was at the end of Unit 4 that we were doing two-body problems. Now here they are again, only now we have acceleration instead of summations that equal nothing, they equal ma. So sketch the force diagrams and sketch the drawing. Opposite order, drawing first, then force diagrams, and then turn the video back on. So I'm just going to keep going because I don't need to pause it because you're going to pause it. So for the car, here we go. We have a force of gravity on car. I'll just label it FGC, force of gravity on car. And we have a force of ground on car. Oh boy, I guess I'll say force of GROND on car. So force of ground on car, force of gravity on car. And of course we have a force of rope or tension, or is this called is it a rope? A rope, yes, force of rope on car. All right, so that's what we know. That's what we have happening. It doesn't say anything about friction. It says the car's in neutral, so it's going to roll easily. So we're just going to assume then this whole situation is frictionless because they haven't told us otherwise. Force diagram for the rock. Oh, I don't want to put that there. Let's go right here. So, force of gravity on rock and force of, oh boy, force of rope on rock. Oh gosh. FRR. Oh, F of rope on car. How about that? Okay, now that's what we have, right? Oh boy, these are yeah. Yeah, I'm not sure if this is great or not, because here's the deal. This force diagram right here. Well, first of all, is this one showing balanced or unbalanced forces? I hope you're thinking that it's showing unbalanced, because again, we have something pulling to the right, nothing pulling to the left. We're unbalanced to the right. Now, force of gravity on the car, those should be balanced. And if you want to show that by some congruent lines, go right ahead. This, what I'm not sure about is if I've drawn these well enough. In other words, is this supposed to be balanced right here? I hope you're thinking no, because what's this whole thing going to be doing? This whole thing is going to be accelerating as the car rolls toward the edge of the cliff, and the rock, of course, then begins to fall. That means that these two forces cannot be the same size. Now, they're not in my sketch here, but they're maybe too close to the same size. I don't know, it's hard to say. And I probably at this point can't Of course I cannot erase it. Of course not. So I'm just going to do this. I'm just going to say, hey, that is bigger than that. Ooh, that. Oh gosh. Things are moving. That's bigger than that. There we go. So the FGR is bigger than the FRR. Otherwise, it wouldn't be accelerating. Okay. Now, where do we go from here? We have two summations. At this point, we don't really care a whole... Well, oh boy. This is where things start to get a little bit confusing. Now, we've done this before, so follow with me here. We have done this for two-body problems. You probably don't remember, but I don't know. We have pretended before to swing this thing out like this. Oh, why is that doing that? Let's try this again. Swing this thing out like this, showing that... Oh boy. Is that pretty good? No, it's not terrible. I'll tell you that. So that here's what's happening. The rock is being pulled downward by gravity, this way, which is pulling this way on the car. So let's just pretend that this whole thing is doing this, okay? This rock is being pulled this way by gravity, which means that this whole force diagram, it kind of needs to, rotate around so that the force of gravity on the rock is actually not down, it's actually pulling this way, so that our rope isn't having a direction change at the edge of the cliff. It's just all straight out in one direction or one dimension. So here's what I'm thinking. And again, we've done this before, but it's been a little different than it is now. So that means we have force of gravity right here on the rock. And then we have force of, oh boy. We have force, oh gosh, of, what'd I say? Rope on the rock. That now is in the right orientation compared to the car. So we want the rock and the car to be in the same orientation so that the directions match up with what we see over here. That means we kind of can ignore the force of ground on car and the force of gravity on car, because those are in the vertical plane, and that's not the direction the car or the system is moving. We can just pretend the whole system is going to be accelerating to the right in this case. All right? So I hope you're still following with me. So really, this part here, we can almost ignore those at this point, because they're not going to be in the dimension that the acceleration is happening in, and so we don't really care about them. Now, that means that for the car, I want you to think about summations here. For the car, why did I tell you, this is just not my day, and this video is probably going to be forever long because of all of this. So the sum of all the forces on the car is just the rope, force of the rope, and that's going to equal ma. But m, we're talking about, is the mass of the car, mc times a. And I suppose we could say force of rope on car. And over here, for the rock, we have a summation of forces. Oh boy. Summation of forces. And that would be the force of rope on rock plus force of gravity on rock equals mass of rock times A. You getting all that? That's an equal sign. Oh, geez. That's an equal sign, not a 2. Look at 2. Boom. Got it. All right. So we have two summations, one for each one for each object. And I suppose we could even do this. We could even notate that's the sum of forces on the car. This is the sum of the forces on the rock. Now, we have two equations, if you'll notice. We have an A in each. Are those two different A's, or are they the same A? I hope as you think about it, you're thinking that they have to be the same A because these two objects are connected by a rope. Therefore, since they are connected, they have to accelerate at the same rate. That would be very... If they were accelerating at different rates, then they would no longer be connected. So, I hope that makes sense. So we know that this A is the same as this A. Okay, so that helps. We know the M of the rock. We know the M of the car. Okay, so A is really what we don't know, which I think is what it's asking for. What is the acceleration of the car toward the edge? So that's what we want to know. We know the mass, we know the mass. Do we know the force of the rope on the car? Do we know the force of the rope on the rock? Well, no, we don't. Do we know the force of gravity on the rope? I mean, rock. Wrong R. Sheesh. Why didn't I call it like cable? No, because C, and then the C here. Oh, gosh. Why didn't I call it tension? Force of tension. Yeah, I should have done that. My apologies. Force of rope on rock. We don't know. We do know the force of gravity on the rock, though. So follow with me here. We know this. We know this. We know this. But we don't know the A's, and we don't know the force of the rope on the car or the rock. Now, here's what's happening. We have two equations and two variables. That's a variable. Maybe if the, oh my gosh, this thing is, I'm trying, oh, I swear. Are you, what in the, there. That's a variable, and that's a variable. That's a variable, and that's a variable. Everything else we know. So, if you have two equations and two variables, you can solve one equation for one variable. It looks like we have three variables. Maybe you're thinking this. Maybe you're thinking, Mr. Dublin, that is the force of the rope on the rock, and that is the force of the rope on the car. Those aren't the same variable. So don't we have three variables? One here, A is the same for both, and then F here. No. See? And here's the thing. I want you to think about this. The rope is the mechanism by which the car is pulling on the rock, and the rock is pulling on the car. Did you hear what I just said? The rope is just the mechanism by which the car is pulling on the rock, and the rock is pulling on the car. Think about this. Force of car on rock. Force of rock on car. That's a what? Are you thinking? I see. I don't know if you just said it in your brain, if you said it out loud. So the force of car on rock, force of rock on car, that is a force pair. That's a force pair, which means they're the same amount, but they're in opposite directions. Oh. So what does that mean? Well, that means that this, the force of the rope on the rock, is the same as the force of the rope on the car. It's the same amount of force. They happen to be in opposite directions. The rope is pulling the car this way, but it's pulling the rock this way. It's pulling this way to the left on, or I mean up technically, but when we adjust the directions here, it's pulling to the left on the rock, but it's pulling to the right on the car. Equal amount in opposite directions in different force diagrams, different systems acting on each other. Okay, so we can just get rid of, it's no longer force of rope on rock or car, it's just force of rope. I mean, oh my gosh, did I say force of rock on car? Force of rope on car or force of rope on rock. That's gone now. It's just a force of rope. One of them happens to be the opposite direction of the other. This video is taking forever. I apologize. So now what? Well, here's what I would suggest. Now again, this is one way to do. This is the more complicated way to do this. I'm going to show you. In fact, hold on. I need to duplicate. Oh, dude. No, never mind. This is the more complicated way. I'm going to show you a simpler way here soon. But let's just start substituting in some stuff. All right. What do we actually know? Well, we know. Let's make it red now. We know that the FR is the same as the other FR. We know that this is 1,000 kilograms. And we don't know A. We know here that the FR is the FR. I mean, we don't know what exactly that is. We know that the FGR is actually 500 newtons. Well, isn't it negative 500? Well, no, because look what we've done. We changed the direction. It's to the right, and to the right is positive. To the left is negative. So because we're saying that both the rock and the car are in the same system, well, not necessarily the same system, but the same scenario, we need to make sure that their directions match up. So down for the rock is actually to the right for the car. So that's a positive 500 then. And that equals the mass of the rock, which is 50 kilograms, times A. Now, again, notice we have two equations. We have two variables. And look at this. The one on the left, it's already solved for the force of the rope. So we can just substitute this in where? Right there. Do you see what I'm doing? So, now I'm going to run out of room pretty quickly. So this is going to be, oh jeez. So it's actually 1,000 kilograms times A plus 500, oh boy, that's a plus, 500 newtons equals 50 kilograms times A. Now, what? Oh, no, I almost forgot something. Negative. I have to put the opposite sign there. Why? Because notice our two diagrams. This one's to the right. This one's to the left. So that means the force of rope on the rock is actually the opposite direction of the force of the rope on the car. So it's the negative of this. If this is what the force of the rope is on the car, then the opposite of that has to be the force of the rope on the rock, if that makes sense. I hope that makes sense. Then, you see, you can, I suppose, add the 1,000 kilograms times A to the other side, right? That becomes 1,050 kilograms. Yeah, you still with me? So that is 1,050. Oh boy, this is bad writing. 1,050 kilograms times A, and that equals 500 newtons. And then, of course, you divide those, and you get A is, what did I write down here? 0.476, 0.476 meters per second. Ooh, squared. Oh, geez. Oh, that's even worse. What's happening right now? Oh, gosh, forget it. Just forget it. Meters per second squared. Okay. So, yeah, that's the acceleration. Oh, my gosh, we haven't even figured out part C yet, and I haven't even shown you the easy way. Oh, gosh. So, that is the acceleration. Kind of, I don't know. I don't know if this makes any sense or if it doesn't. Let me show you what the easy way would be. Okay? Let me show you the easy way. This is when we looked at both objects as their own system. Okay? Again, we had a summation here, and we had a summation here. Two separate systems. One for the car, one for the rock. What if we view them as the same system? All one system. Well, that would mean, hold on, let me switch to the next slide here. Let me get a fresh, clean slide. Okay, so that would mean, in this case, that if we're going to do this little situation here, just pretend that that's a big old rock. So if that's terrible, the other slide was much better. Much better. So if we say, hey, this whole thing is our system. The whole car-rock combo is our system. What's the only force that's acting on our whole system? I hope you're thinking about that, and I hope you're thinking that it is the gravity force that's this way. Gravity force on the rock is to the right is the only thing acting on our system. Now, okay, yes, we still have the up and down. Remember, for the car, we had the gravity down, we had the ground up, we had the rope to the right, and then again, the rock, we had the rope to the left and the gravity to the right. But remember, these aren't here anymore because those are a force pair that are actually inside our system now. See, the force pair doesn't exist anymore because we're not looking at them as separate systems. We're looking at them as a whole system, and the force of the gravity on the rock is the only force we have now that's acting on the whole system. So let's think about that summation. Well, that is, sum of forces is FGR equals what? The mass of the whole system, oh dang, the mass of the whole system times what? A. Do we know what FGR is? Yes, it's a force of gravity on a rock, which is 500 newtons. 500 newtons equals 1,050 kilograms times A. And A is what? 0.476 meters per second squared. Now, I believe that it's the same thing we had on the other side, only it was a mess over there, if you remember correctly. So here's what I'm going to suggest, okay? I mean, you can look at it the other way. I would suggest that you view two-body problems like this, when there's two different things that are connected by a string, view them as one whole system. But you're going to have to, rotate the objects around so that when you draw or when you think about the system as a whole and the force diagram of that system, that it will show both of the objects moving in the same dimension. Like I believe number 8. Number 8, you have a pulley. And the pulley has a string like this. And you're going to have what I would say is showing a dashed line like this. Say, okay, there's one object. And then you're going to have another one like this. And then the object like so. And so that will give you the ability to look at this as two objects that are moving one way or the other, depending on which object is more massive, in the same dimension. Okay, so again, you're going to have to rotate these strings so that the objects in the system have the same orientation. Now let me just erase all that. We're coming to a conclusion. It's okay. It's okay. Relax. Go get another cup of coffee. Let's see, where was I? Oh yeah, we had to find out how long do they have to apply the brakes before it's too late. Now, what we do know is this. We know that they are 10 meters away from the edge of the cliff. We know they're accelerating at 0.476 meters per second squared in the positive direction. Notice it's positive, and positive for us is the right in this case. So how long do they have to get from here to here? Well, let's make a list. How about that? Do we know delta x? Yes, that's the 10 meters. 10 meters. Do we know a? Yes, that's the 0.476 meters per second squared. Do we know the VI? Yes. VI is what? Well, I assume they're starting from rest. So that's 0 meters per second. Do we know the VF? No, we do not know the VF. Do we know the delta T? No, we do not know the delta T, nor do we care. So is there an equation that we can use that has those three variables that we can figure out how long they have? Oh, I said that we don't care about the time. Of course we care about the time. It's the VF we don't care about. So we need the delta T. Is there an equation that has delta T in it, doesn't have VF in it, but has VI, A, and delta X? Why, of course there is. I hope you're thinking about which one that would be. Delta X equals VI, oh boy, come on, delta T plus, oh gosh, plus 1/2 A delta T squared. There we go. Hope that's one you're thinking of. Now you just plug the stuff. We know that it's 10 meters. We know that VYI is 0, so that whole thing goes away. And we know 1/2, and we know that it's 0.476 meters per second squared, and we know that we're looking for the delta T. Don't forget that you squared that. Some of you have forgotten in the past that there's a square there that's going to have to be taken care of later. And so you do all that math, and you find out that the delta T is, hopefully anyway, 6.48 seconds. That's how long they have to be able to put the foot on the brake, or that car's going off the edge. I hope this helped. I mean, geez, kind of a long video. But hey, that's it. That's how it works. Now, again, I don't care which way you view it. You can view it as two separate systems. Again, there is some extra work involved, but I hope you noticed that what this got us down to by doing this as a single system. I want you to look at the work that hopefully you already wrote down. This is what we ended up with in the final step. After combining the two equations, solving the one, substituting in the other, we still ended up with 500 newtons equals 1,050 kilograms times A. Like, that's what it came down to. And again, it did that because this force and this force are a force pair that we lose. It's gone when we take two separate systems and combine them into one system. I hope that makes sense. So we're actually getting rid of these two forces that were separate, one in each diagram, that are gone when we combine the two objects into the same system and view it as a whole. But again, remember, that means the mass you're dealing with is the whole system mass and not one or the other object. It's both. So there you have it. If I were you, I'd be trying numbers 6 and 8 and seeing how those go. I can post the key to those as well, so you can take a look at that. And again, like I said in a post on Classroom, we've got worksheet 4, which has some more practice of these kinds of problems, and then a review, some The review is odd. It's a little more, it's not quite problems. It's more like, hey, you need to know how to do this. You need to remember how we did this, that kind of stuff. There are a couple of problems, but most of it is know how to do this, know how to do that, blah, 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 blah list. So anyway, I hope you all are well. And if you would like us to do a Google Meet at some point, so we can kind of get any questions cleared up or answered more easily than through text, then let me know. Otherwise, stay safe out there.